Okay, so welcome back to this session. So we will be hearing about two other techniques to detect exoplanets. And now we'll start with Jen Burt, scientist at JPL, who specializes in radial velocity studies of exoplanets. So take it away.
Okay, can folks hear me through the mic? Wonderful. Good morning, everybody. Welcome back. I hope we're all happily sugared and caffeinated at this point. It is my absolute pleasure to be here today to talk to you a little bit about radial velocity detections of exoplanets. And so I'm going to start with a quote that I think probably every RV scientist in the US has used in a funding proposal at some point in their careers by now. Which is from the 2018 National Academies of Science report, which highlights that mass is the most fundamental property of a planet, and knowledge of a planet's mass, along with something about the radius, is essential to understand its bulk composition and to understand spectroscopic features in its atmosphere. And so this has been borne out by work over the last 6 years or so. Natasha Batalha has a nice paper highlighting the fact that if we take transmission spectroscopy of our planets using facilities like the Hubble Space Telescope or the James Webb Space Telescope, and we want to then accurately interpret the spectroscopic features we see, then we need mass precision at least the 50% level for our hot Jupiters and hot Neptunes, and something closer to a 20% mass precision or a 5 sigma mass measurement for temperate planets, smaller planets than Neptune. We also need precise masses if we want to think about the interior compositions and core mass fractions of our planets. And so again, here, work from Schulze in 2021 highlights that, again, 20% mass measurements for small planets are required if we want to characterize their interiors, but this is dependent upon also understanding the chemical composition of the host star, things like the iron and silicon abundances of that star. We're starting now to also think not just about transmission spectroscopy, which has been the predominant way that we characterize exoplanet atmospheres over the past decade, but now about reflected light spectroscopy. And this is the goal of the upcoming Habitable Worlds Observatory, or HWO, where we're aiming to actually block out the light from the star and image the planet itself. And some early looks at this by Mario Damiano, also at JPL, suggest that we need mass uncertainties at the 10 sigma level, 10% precision, if we want to be able to accurately identify the secondary gases in the planet's atmosphere. And so for Earth, this is like understanding that, yes, there is oxygen in our atmosphere. There's also a whole lot of nitrogen in the atmosphere. And if you can't tell if that secondary gas is nitrogen or something else, it adds questions about the potential habitability of the planet. Now, all of these works are focused a bit more on the individual characterization of planets once we've already detected them, once we've put in proposals to get atmospheric spectra of them. But more generally, as we think about the detection of planets as a population, I like this plot from Zhu and Dong in 2021, which shows the different sensitivities, different discovery spaces of the many types of exoplanet detection efforts that we'll be hearing about this week. And something that shows up here is that, as Josh mentioned, for transit spectroscopy, especially from the ground, we're looking mostly at larger short period planets. With missions like Kepler, we have a longer baseline, but still a bit of a cliff as we move out in semi-major axis space. But with radial velocities, we have the capability to find lower mass planets out to longer periods. And that's because we are far less constrained by the orbital geometry of these systems. Radial velocities have a nice aspect where we can detect planets on most inclinations around their stars. There does become a point where you can't actually see the reflex motion that the planet induces anymore if it's a purely face-on orbit. But we have a much broader range of sensitivity, which helps us in tracking down planets. This is especially nice when, again, as Josh mentioned, the transit method, we can look at hundreds of thousands of stars at once. Radial velocities, we're often looking at one star at a time. And so we trade off a little bit in our detection efficiency by being able to be sensitive to more systems. Okay. And so this is become an important aspect for NASA as well, which despite being a very space-based agency, as the name implies, and as our arc of exoplanet-centric missions here on the top makes clear, has a growing interest in ground-based astronomy efforts as well that support these space-based missions. And so you can see on the bottom of this nice figure, all of the different ground-based telescopes that NASA has invested in. And all of these either already have or will soon have a precision radial velocity instrument attached to them. And we're trying to make good use of that. So like transits, radial velocities are an indirect detection technique. We never actually see the planets. Rather, we see the impact that the planet has on the host star. And so to walk through that a little bit, we're using the fact that when light forms inside a star, it generates a continuous spectrum, the full gambit of our colors. And then as that light progresses through the outer cooler layers of the star, it interacts with different elements and molecules that are in the cool layers of the star. Those imprint onto that spectrum, and they produce these dark lines we call absorption features or absorption lines in the spectrum by the time it gets to Earth. We get lines both from the atmosphere of the star and from the atmosphere of the Earth as we come through to our ground-based instruments. Those are called telluric absorption features. And so by the time it gets to us, we have this very nice chemical fingerprint of the star. And I want to take just a very brief aside to say, well, I showed this very cute kind of ground-based or a backyard scale telescope here. The instruments that we actually use to do this are what we call Echelle spectrographs. And so instead of just measuring the brightness of the star in a wide bandpass and tracking that over time like we do with the transits, here instead we are taking the light and dispersing it twice. So the light comes into our telescope. It passes off in a shell grating here, which splits it into our Roy G. Biv rainbow of colors, and then it gets cross-dispersed, so it ends up producing kind of this grid form of a spectrum, what we call an eshelle. Eshelle is ladder in French, and you can see why, because when we look at the actual observations, we have these nice ordered rungs, or what we call orders, and each of these is a chunk of the wavelength. And what we end up with is the wavelength of the star, which are these solid-ish lines here. You can see the absorption feature standing out as the black spaces. And then the dots up above are lab-based reference for the wavelength calibration of the instrument. I can talk about in that more detail later on if folks are interested. But going back to our cartoon picture of what the spectrum of the sun looks like, we again have a full rainbow, and then very specific lines that tell us about the chemical composition of the star. That is well and good. People spend careers doing very detailed synthesis work to understand why certain elements and molecules produce certain lines. But the thing that I'm more interested in, and the RV community as a whole, is what happens when these lines start to move. And that movement is often induced by a Doppler shift in the star. So does anyone know what the normal kind of canonical example of a Doppler shift on the Earth is that we see most days? You all just had coffee. Come down. What? Not enough coffee. What is the example of a Doppler shift that we interface with on a day-to-day basis? A passing car. Oh my God, you're so on track. This is great. Okay, so yes, in my very cartoon example here, the Doppler shift that most of us encounter in our normal lives is that as a car comes towards you, if it's beeping its horn or has a siren or something like a fire truck, as the car approaches you, the Doppler shift of the sound, because the object producing the sound is moving towards you and crunching the sound waves together, causes the pitch to go up. And then as the car goes by, it causes the pitch to drop down because now the car is receding. And so the pitch, the frequency is dropping down. And so in light, we see a very similar thing. And so this is dependent upon both the source frequency of the horn itself on the car, our velocity as an observer, here we're standing still, and then the velocity of the source as it first approaches and then moves away from us. And so what this translates to in a light sense, if we look at a real Echelle spectrum, this is taken of the sun with the Automated Planet Finder, a telescope up at Lick Observatory in California. What this looks like in a Doppler shift is that all of our little absorption lines move back and forth. This is wildly exaggerated and not actually what this looks like, but just to give you a sense of what we're talking about here. If we think about the physical cause of this, one reason that we see periodic Doppler shifts in a star is if there's a planet orbiting around that star. The gravitational tug of the planet causes the star to make a much smaller orbit in the middle of the system. And what that does is, from our perspective as an observer, means that the star is alternately coming towards us and then moving away from us and then coming towards us and then moving away from us. And that change in the radial velocity, the velocity in the radial direction of the star, imparts these Doppler shifts. And we can measure the shift in the wavelength and then translate that to a velocity of the star, the v in our Doppler shift equation up here. Now, if you measure the radial velocity of an object on a circular motion over time, and then plot that as the orbital phase of the planet, or in the star in this case, what we see is this idea of the star is moving away from us, so it is red-shifted, and then it turns around, it passes through 0, it comes back towards us, so it is blue-shifted, and it plots out this sine curve type shape. Getting into the exact characterization of the orbit is not something I'm going to spend a lot of time on here, but there are 7 elements that are necessary to define that Keplerian orbit of the planet. The first 4 are the more physical side of the parameters. It's the semi-major axis, its distance from the star, the eccentricity of the planet, the period, the position at pericenter. And then the other 3 are angles that are all based on your orientation to the system. And so again, this is dependent on where you as an observer are with relation to the star and how the projection of that orbit appears on the sky. And that tells you something, or that defines how that orbit appears to us. The parameters that we actually derive when we're fitting RV data are a little bit different than this. And so when you're reading papers describing radial velocity planet detections, the thing that you'll see people quantify are the period again, the semi-amplitude of the planet, that's the size of our sine curve, and I'll show that in a moment, the eccentricity, the longitude of periastron, the time of periastron, and the mean anomaly. And so to walk through those, if we look again at our synthetic RV curve here, the orbital period is just the period of our sine curve. The semi-amplitude is the height or the half height of the sine curve here. Those are related to one another via this equation, which is dependent upon the period of the planet around the star, the mass of the planet, and the mass of the star, and the orbital eccentricity. And so if we can measure K, we know the semi-amplitude, and if we separately have determined the mass of our star via stellar characterization efforts, and we measure the period, then we can work out what the mass of the planet is. Now, what those parameters do to the shape of a radial velocity orbit for the first few is, sorry, keep clicking the wrong button, is shown here. So the period just sets the period of your sine curve or your Keplerian. So shorter period means more frequent oscillations. The semi-amplitude sets the scale of your sine curve. So higher semi-amplitude means bigger sine curve. And then the mean anomaly sets where the 0 point of your radial velocity is. So based on this green dotted line, you can see that these 2 curves are just shifted a bit with reference to one another. The 2 parameters that are more interesting in a sense and have a bigger impact on our radial velocity curve shape are the longitude of periastron and the eccentricity of the planet. And so for a 0 eccentricity case, which is the left column here, you can see that we have this kind of nice, looks like a sine curve or a cosine curve, depending on how it's phased. But when we get to the higher eccentricity cases over here, we end up with these radial velocity curves that can be flat for long durations of their orbital period, and then have very abrupt departures, very abrupt spikes that show up as the planet's influence on the star. Okay, so the way that we actually measure these planets or detect these planets, if we have radial velocity data, that again looks roughly like a sine curve in orbital phase or time space. In an idealized scenario, you have a perfect sine curve here caused by your planet as we measure the velocity of the star. We take a Fourier transform of that very nice sine curve, and it gives us this very precise delta function in our frequency space that says this is the period, the frequency of your planet. Unfortunately, because observing doesn't work that cleanly, and often when you apply for telescope time, you maybe don't get all the time you asked for, or things happen like the sun comes up and so that causes problems with observing, or you get weathered out, or you go to attack and say, I would really like to observe my 7th magnitude star during dark time, and then the galaxy folks who want to observe their 20th magnitude extragalactic source are competing with you and they get preference because honestly, that's kind of fair. What that means is that you end up with a much more uneven sampling of data that looks kind of like this. And so we use something called a Lone-Scargill periodogram or similar techniques, which can handle unevenly sampled data to take those radial velocity points and then look at what peaks emerge in period or frequency space. And so what you can see here is that things get a lot messier, a lot kind of scruffier in our periodogram space, but we do still have this nice signal at around 38 days that stands up as kind of a independent peak that rises above the various thresholds we set for the false alarm probability, or FAP, which tells us that we think this is a real signal and not something caused by statistical alignment or of our random, not randomly, but of our data points. And so if we take that period of 38.14 days and we phase fold our data to it, what we get then is, again, this nice alignment of here is the Keplerian curve that defines our planet, and here are all the data points that sit nicely along it. Often the first question you get when you describe how radial velocity fitting is done is, well, what happens when there are multiple planets in the system? Because it's all well and good to look at a data set and kind of see a sine curve, but if you have multiple planets that are all pulling the star in different directions at the same time, how does that show up? And so this is a traditional way to do this type of search. Nowadays, we use better techniques and more nuanced techniques, but I think it's a helpful illustration. So this is real data from a K-star that we observed first with the high-res spectrograph in blue, and then with the APS spectrograph in red. And we had been looking at this, as you can see, for many years at this point. And when we looked at the periodogram of the data, we saw this big peak at 202 days. So we said, okay, we think there's a planet here. You can then fit your Keplerian curve to that period, phase fold the data, and say this looks like a planet. We then take that signal, we remove it from the data. We say, yep, this one's good. And then we look at the residuals of our data once that signal is removed and make another periodogram. And here we see that there's a signal again at about 1100 days. So we phase fold our data to that signal. We say this also looks pretty robust. We like this signal. We set it aside. We now remove both planets from our original data set. And then we keep doing this iteratively, finding more and more signals that look okay. This last one, you can see the peak doesn't quite rise above our false alarm probability threshold, the solid line here, but that's because it's almost a 4,000-day signal. And so most of the data is only covering one part of the sine curve. So we don't have, we have a few points that are fully closing the orbit over here, but in general, this is a bit of a stretch given the baseline of the data that we're working with. And then eventually you get to a point where you take the residuals, you make a periodogram, and there are no more significant signals. And then you say, okay, we think we are done now. You can then model that system. And here, this is a nearby K-star that we think has 4 planets around it. They're shown as the red circles. The dotted lines are our own solar system. So Mercury, Venus, Earth, and Mars, and then Jupiter out here. All of these planets are much larger. They're like Saturn mass planets going around the star, but there is kind of a cute alignment between having 3 inner planets close to our own terrestrial planet orbits and then 1 outer planet close to Jupiter. I will encourage you, if you are interested in the nuances of more advanced or more modern RV fitting, BJ Fulton, who is speaking on Thursday, I think maintains one of the better RV fitting programs called Radvel in the community, and you should bother him for more details about how that works. Okay, so that is the very basics of how we detect RV planets. I want to spend some time now on what we can currently detect with this method. And so this figure shows all of the planets in the Exoplanet Archive that are confirmed and published and have RV masses of at least 3 sigma, I believe was the criteria I set here. You can see that in the early days of radial velocities, we start with planets that have semi-amplitudes of kind of 10 to 100 meters per second. And then we rather rapidly advance down over the following 10 to 15 years to detecting planets that have semi-amplitudes of about 1 meter per second. And then things kind of stall out for a while, and we'll get into that. But so some nomenclature for the field is that 1 meter per second detections, 1 meter per second semi-amplitudes of planets is what we can do now. We do that pretty robustly in the field, and this is precision radial velocity. What we're aiming for when we think about looking for Earth twins, so an Earth-sized planet on a temperate orbit around a star like the sun, is 10 centimeter per second precision. That's what we in the field call EPRV. And then there's kind of this squishy space between there, detections in kind of the 30 to 50 centimeter per second range. This is the current bleeding edge of what the field can do now, and what I often refer to as E in parentheses, PRV. So we're working our way down, but it has not been a single leap. Maybe unsurprisingly, there's a lot of little steps that are taking place as we go from the yellow to the purple. If we put those detection thresholds on top of all of the planets that have been confirmed, you can see that they form these nice diagonal lines as a function of orbital period and planet mass. Again, many of the RV detections, the red points here, are up above this 1 meter per second threshold. But again, we can see more of them that are pushing down to this 30 centimeter per second threshold. You might note that as of yet, we don't yet have planets via transits or radial velocities down near either Earth and Venus as our representative temperate terrestrial planets, or out at the orbits of Uranus and Neptune. And generally, that is because planets in the upper left of this figure are easier to detect. They have shorter periods, they have larger masses, and so based on our RV semi-amplitude equation, they are bigger signals. And then the planets in the lower right are harder to detect because they have longer period orbits, they have smaller semi-amplitudes, they are more challenging. The different factors that impact the precision of our individual radial velocity measurements, so not the measurement of the planet mass and its semi-amplitude, but actually the individual RV points we use, can be broken down into 3 main contributions. You have the error from the photon noise of your observation, which is based on the star you're observing, the telescope you're using, the exposure time you set. You have the error from the facility or the instrument you're observing, which has to do with the stability of your instrument, your capability to calibrate motions in that instrument and to calibrate the wavelength solution correctly. And then you have contributions from the star itself. And this one will trigger a bit of a fight in the community over whether this should be a source of noise or a source of signal. We're working hard to treat more aspects of stellar variability, like signals that are modeled and removed from our data nowadays, as opposed to just noise that we sweep under the rug. This is a nice landscape of the current high-precision Doppler spectrometers that are in operation around the world right now. You can see that they're broken a bit into a set of visible instruments. This is where most of our very high-precision work is being done. These are more focused on sun-like stars. And then near-infrared instruments over here, these are more focused on M-dwarf stars, redder, cooler stars. They often don't achieve quite the same precision as the visible instruments, in part due to the information content of the spectra themselves. But there's a trade-off where stars tend to exhibit less stellar variability in redder wavelengths. And so we're trying to find the sweet spot between the different wavelength regimes, the different types of stars we're observing as a community. The stars themselves set a lot about how much RV precision we can squeeze out of them. Things like the effective temperature of the star and the metallicity both impact how many spectral lines are available for us to look at and try to measure these tiny shifts over. Things like the rotational velocity impact the broadening of those lines. Broader lines are harder to measure tiny shifts, and so we like slowly rotating, cooler stars that are very bright. That is very nice for us as an RV community and what we strive for. The uncertainty contributed by the instrument is often broken down into aspects about the stability, both thermally, vibrationally, and with regards to pressure of your RV spectrograph, things about how your calibration is working, things about the detector itself, pixel offsets or pixel tracking. And so those are often, for modern day instruments, we're aiming for error budgets across the whole instrument of something like 30 to 40 centimeters per second. That's what's being achieved with the most recent generation. And that tens of centimeters per second is important because if we think about the actual scale of what we're trying to do, if we're trying to push to longer period planets and smaller planets, then there are 2 big challenges. So to start with just the RV scale of things, if we think about Jupiter orbiting around the sun, the barycenter of that system is a bit outside of the sun. The semi-amplitude here, again, this is the equation I showed earlier. And if we plug in some numbers for the mass of Jupiter and the mass of the sun and the orbital period, and we crunch through some math, what we get is that the semi-amplitude of Jupiter is something like 12.5 meters per second. For me, that's not a particularly intuitive number, but my favorite reference is that this is about the speed of Usain Bolt coming down a 100-meter sprint in the Olympics. So these stars are moving relatively rapidly towards and away from us. If we translate that to a Doppler shift, if instead of meters per second, we translate that to the actual wavelength shift that we would be observing, and I set the measurement in kind of the green part of the spectrum at about 500 nanometers, because this is where a lot of our visible instruments operate right now, that is a Doppler shift of 2 × 10⁻5 nanometers. It's a small number. If we then translate that to a more physical thing about our detector, and I tell you that this is a 4K by 4K detector, so there's something like 4,600 pixels across the span of the detector, and each of those orders that I mentioned earlier in our shell spectrograph, a single bar across this detector is something like 6 nanometers wide. Then we can relate the shift in wavelength space to a shift in pixels, and this is something like 1/100th of a pixel, 1%, 2% of a pixel. That's a hard measurement to make. You know, it's not something you'll ever see by eye, but we are well capable of doing this nowadays. Tens of meters per second is old hat in the RV community at this point. Things get more challenging when we shift to planets like the Earth, which, despite having a shorter period orbit, is much less massive than Jupiter. And so the barycenter of the Earth-Sun system is well inside the Sun. It makes a much smaller orbit in response to the Earth's gravitational tug. If we fill out the same math that we did for Jupiter, the semi-amplitude of the Earth around the Sun is only 9 centimeters per second. Now, for context, again, Jupiter around the Sun, Usain Bolt sprinting towards you will knock you on your butt if you stand in front of him. Get out of the way. The Earth around the Sun is a desert tortoise, just kind of slowly plodding towards you. Okay? So this is what we're trying to measure, a star moving towards and away from us with the speed of a desert tortoise. If we translate this back to the number of pixels, again, via that same wavelength or velocity to wavelength and wavelength to pixels math, this is 0.0001 pixels moving back and forth across our detector. This is very hard. This is the equivalent of your absorption line moving back and forth across 6 silicon atoms on your detector. Yeah. Thankfully, we don't have a single absorption feature. We have thousands of them that are spread across the entire spectrum, but this gets at the idea of why we take light from one star at a time and spread it out as finely as we do over these very high resolution instruments, because we need to see all of those lines as precisely and accurately as we can. To further complicate things, this, again, 9 centimeters per second is a signal of the Earth around the Sun. Turns out our Sun is a pretty boring, quiet star for being a sun-like star. Despite that, the variability of the Sun, the motion of the Sun due to, well, what looks like motion of the Sun, due to things like spots and plages and magnetic cycles, still has an RMS of about 3 meters per second, 3 or 4 meters per second, even in its quietest period. And so this is solar RV variability after we've removed the signals from all the planets in the solar system, because we know where they are, so we can model that out. And then I've put, I promise you this is indeed a sine curve, even though it looks like a flat line, but that's the Earth's RV signal in the Sun. And so this is what we're trying to do as a field right now when we talk about EPRV capabilities. And indeed, there are a whole lot of different types of stellar variability operating at different time scales and at different RV semi-amplitude contribution levels. And so we're working hard to understand all of these well enough that we are no longer just trying to average over or bin over their contributions, but rather treat them as individual components of our models. And there are a couple ways to go about that. You can try to model here, as you see on the left, the stellar variability in the radial velocity measurements alongside the Keplerian contributions, which are this little green squiggle here. And so we do that by looking not only at the radial velocities, but also activity indicators that help us track what the star is doing. You can also try to separate out ahead of time from your raw RV measurements which part of that measurement is due to shape deformations, changes in the line shape, which are then driven by stellar variability, versus changes, lateral shifts that are actually due to pure Doppler shifts. And then if you can separate those, you work with just the Doppler shift portion of things. And you can see here that applying these types of changes helps increase our sensitivity over, if we look at an orbital period versus planetary mass plot, but down from a factor of 3 Earth masses to about 2 Earth masses if we use this program called Scalpels. There are a lot of different approaches to dealing with stellar variability. The field is working hard on this. And so we are looking at operating at levels everywhere from the radial velocities themselves to the spectra that we derive the radial velocities from. We are still working to identify the most effective solutions, and the answer is likely that it depends on the instrument you're using, the star you're observing, how you design your survey, et cetera. So there's never going to be a single solution to this. It's going to require a comprehensive approach. So to talk a little bit about the state of the field, I have exactly one demographic plot in this whole talk, and it is this one. So this is work from BJ Fulton in 2021. It turns out that doing demographics on radial velocity surveys, especially long ones, is hard because there are a lot of decisions that are made over the course of 10 to 20 to 30 years about which stars to observe and how often to observe them. And we don't like this star anymore, so we're going to kick it out of the survey, but then maybe it's interesting again, so we'll bring it back. And correcting for all of those decisions is quite complicated, but BJ and crew took a good swing at it and managed to do some very nice demographics work using the long-term Keck high-res data sets. And so this shows the occurrence of planets really looking at things above about 30 Earth masses here as a function of semi-major axis. What I'm really excited about is that with the current generation of RV instruments, things that have come online over the last 5, maybe in 10 years or so, there are a number of dedicated surveys that are thinking hard about this problem and trying to be more intentional and doing surveys that are meant to detect smaller planets with more consistent approaches so that it'll be easier to correct for the way you observed, how your survey was designed, et cetera. And so this is just a handful of the ones that are ongoing right now. And there are also a number of additional kind of PI level efforts that are being run on all sorts of instruments. Okay. So ways we quantify the state of the field right now, a traditional approach is to take the RMS, the scatter of your RV time series over a long baseline. Arvind Gupta has a paper that's in review right now describing the first few years of the NUID Earth Twin Survey. It's one of these long form surveys being executed on modern instruments. And you can see that for some of the stars they're looking at, these are all bright sun-like stars that are nearby. We're getting, again, RMS variations down at the meter per second or below level, which is quite encouraging. If we look at just pure RV planet detections, there have been 2 really nice results just this year using only RV. So this is not transit follow-up where we know things about the planet's period and epoch. These are just uninformed RV searches. And so this is a result on HD 20794 on the left-hand side and nearby K-star. And you can see that we're reaching RV semi-amplitudes at the 50 to 60 centimeter per second level, and that the latter or the furthest out planet is at a period of 650 days. So we're really starting to probe low mass planets on orbits even beyond that of the Earth, which is a real step forward for the field. On a shorter time scale, but on a much closer by star, Barnard star has a recent paper from Besant et al. And so these again are RV semi-amplitude measurements at the 30 to 40 centimeter per second level. You can see here that these are much shorter periods. So these are between 2 and 6 day or 2 and 7 day periods. But again, an impressive demonstration of low mass planet detections on M-dwarf stars, which can be more challenging. If we plot the sensitivity of those surveys or those detection efforts, again, using the injection and recovery technique that was mentioned in the transits idea, where you take your radial velocity data set, you inject synthetic planets where you know the right answer for their mass and their period, and then see if you can recover them, that allows us to set sensitivity bounds. And so what we're seeing here is that even at periods of out to about 100 days or so, we are sensitive to masses of, a few Earth masses here. And yeah, like 5 or so Earth masses for the Besant paper. The other big area of improvement is the use of solar radial velocities. So in addition to having RV spectrographs on anywhere from 3 to 10 meter telescopes that we're using at night, many of these facilities have now added much smaller 10 centimeter scale solar telescopes that observe during the day. So you get many hours of very high cadence, very high signal to noise observations of the sun. We can complement that with information from NASA missions like the Solar Dynamics Observatory, which take pictures and magnetograms of the sun's surface and use that to disentangle what is happening. There have been some great collaborative efforts led by Lily Zhao in recent years, where we're taking solar data sets from multiple instruments and comparing them to one another. And this allows us to separate out signals that are communal between the different data sets, which are likely then due to the sun, because we're all observing the same object at the same time. And then signals that are independent, which are likely due to your instrument. So this is a way to get a better characterization of how your instrument is behaving and trust that the signals you're seeing are due to the spectrograph or the telescope and not the star you're looking at. Okay, major challenges in the field. If we go back to the idea of trying to look for a solar system a bit like our own, where we want to be able to see these long period giant planets and these temperate terrestrial planets, there are two different directions to push this. And so one is that longer surveys or just continuous RV surveys where we keep looking at these stars are important to reach out to long period planets. Just for reference, this is the amount of time we've been doing RV since 51 Peg B was discovered. We're not even out to Neptune yet. We could not see a full orbit of Neptune given the baselines that we have right now. And so maintenance of our archival radial velocity surveys, the ones that started a couple decades ago, finding ways to get those to cooperate with the more modern surveys, which often involve some level of overlap observing if possible, so that you set the offsets between the radial velocity data sets is very important. And also just, like having this continued support for long-term surveys, which are unlikely to bear immediate scientific fruits. You're not going to get quick publications out of this, but they're the only way to really probe these outer regions of these stellar systems. And then the other direction to go from our kind of 1 meter, 50 centimeter per second detection capabilities nowadays down to Earth and Venus is this push towards extreme precision radial velocity. Turns out the challenges there are exactly the sources of noise I mentioned earlier, and there's a lot of work to be done in literally every one of these areas. So there are contingents of the field who are thinking about better ways to select stars and match those stars to specific telescopes and design your survey so that you have the right cadences to actually probe all of the different types of stellar variability you're fighting against. There are many folks thinking about the instrumentation challenges, how to build better, more stabilized spectrographs to go after these stars and resolve smaller signals. And then there is just copious amounts of work on the stellar variability front and different ways to model, mitigate, remove the stellar variability. One of the things, oh, I lost a slide somewhere. Well, darn. There's a nice report from the EPRV working group that outlined a roadmap for the next 5 years of different things we should take on to try and improve our detection capabilities. It's a good read. The report itself is quite long, but there's a nice appendix in the front that's like 6 pages. And so it gives you an overview of where experts in the field from all sorts of different observatories and science groups thought we needed to head in the near future. And so I encourage you to take a look at it. One of the recommendations was to build a research coordination network to encourage more collaboration and communication between different RV groups. This is something that I head nowadays, and so I'm going to take a 30-second plug here. If you were at all interested in EPRV, which is a field that, again, has a lot of challenges to face, but a lot of exciting potential moving forward, I would encourage you to either chat with me more or Google EPRV Research Coordination Network. It should show up. We do things like hold community discussions about how to move the field forward. We hold colloquium series featuring both early career and senior career people. We do workshops on EPRV interfaces with things like machine learning or heliophysics. We just launched a networking program called Wavelengths that I'm just very excited about the logo for, so I wanted to include it. But in general, the field as a whole is working hard to push forward, and we would love for any and all of you to be a part of that effort. So with that, I will say thank you so much for your attention and ask for any questions.
Thank you very much, Jen. So we have 5 minutes for questions. We can start here. Yes.
Thank you. Great talk. I wanted to, the question I had even before your talk to Professor Wynn was about how AI is helping improve planetary resolution and all sorts of things. Could you elaborate on how deep learning, because I saw it up there at the 9 o'clock one, right?
Yeah.
So, and I asked that of ChatGPT, so I'll give you the answer.
Oh, goodness, ChatGPT is going to be better at it than I am. We're exploring this in a variety of ways, and it's not something I work on actively. I think Josh actually has a grad student who's been doing some very compelling work in this area, so you should bother him at a coffee break about it. But we're working hard to feed it these large stellar data sets that we're collecting now, and then try to identify via convolutional neural networks, for example, what variations are due to the star versus the instrument versus the planet. And so It's coming into play in a variety of ways, and we're trying to look at things both at the spectral level, at the cross-correlation function, which is how we actually measure the shift level, and at the radial velocity level. And depending on what data product you are working with, there are different ways to try and apply machine learning tool sets and even like large language models nowadays. BJ Fulton also is very keen on this idea, so I would encourage you to catch him at some point. I think not so much on the target selection side, because we are focused as a community in many ways on looking for Earth twins, we tend to select stars like the sun that we know enough about to say that their variability is amenable to these very precise RV searches and their temperature and metallicity are appropriate to it. So the target selection, I don't think is much. I could imagine nice interfaces with the survey design aspect and trying to make sure that you're catching the appropriate cadence and scheduling of your observations, that AI could have a role.
All right, thank you. So let's move to a question online.
You have a question online about, given that brown dwarfs often exhibit atmospheric inhomogeneities such as spots, clouds, or temperature gradients, analogous to sunspots on stars, how reliable is the radial velocity method for detecting companions around them for brown dwarfs?
We don't really do it right now. They're too faint. Is the basic answer. So we're really, for doing precise RVs especially, we're looking at stars brighter than like 10th magnitude or so, and our brown dwarfs just are not bright enough for this. If and when we have large enough scale telescopes, then yes, understanding the variations of the atmospheres of brown dwarfs over time would be an important component of things, but we're at least a generation or two away from that, I would imagine.
So there is another one.
I have a question, actually.
Please.
Okay, yeah, and then I would encourage early career scientists to ask questions, okay? So think about the question while Elise asks.
Sure. Like for this long period, for example, like Neptune's, whatever, let's say 30, 40 years, like what would be the ideal cadence to observe them? Because you don't want to do it every night, but once a month or once a year even, I don't know. Yeah,
so we've thought about this a little bit, and you're right that we don't need nightly observations if the goal is to detect a very long period, beyond the snowline planets. If you also want to look for shorter periods, smaller planets in that system, though, because we think planet multiplicity, if you find one planet, there are probably more, then we do still encourage you to think about, if I want to be sensitive to small planets in the temperate zone, maybe not Earth mass, but even like Neptune mass things, I want to cover that time scale, at least every 10th of the orbital phase or something like this. If I want to also sample the rotational modulation of the star and maybe the decade-long magnetic cycle of the star, so you can identify the different timescales that you care about and then try to construct a survey by combining those. This depends heavily on the capabilities of the telescope you're using, and if it can handle an observing request that is, every third day, please look at this star. That is something that the Q observing facilities have a leg up on, and so they've really proven a powerful tool in the exoplanet RV space.
All right, so time for another quick question. We have 1 minute.
Someone without a faculty position.
Yeah, go. Yeah.
All right. Is this okay? Hi, I'm Ashley. I'm a graduate student at LSU. I was wondering what your thoughts on if you think it'd ever be possible to do RVs from space-based observatories.
I think it is possible. I think, as mentioned with Kepler and TESS, it is incredibly expensive to go to space. It's a whole heck of a lot cheaper to do it from the ground. And again, because we care about this high cadence observing approach, my fear is that RVs from space require you to have a target sample set of like a couple dozen stars. And it's a hard pitch to say, please give me hundreds of millions of dollars to look at these 24 stars. So is it possible? Yes, probably. Also, there's some finickiness with the different wavelength calibration approaches we use right now. They often require someone to go and give them a little love tap every once in a while. And so I would worry about long-term operation of that. We need to really prove that they can be put on a rocket and launched into space and still behave the way we want them to. But more generally, I do think ground-based efforts, in particular, coordinated ground-based efforts, so multiple facilities where you could hand off targets and not be limited by the day-night cycle in a single location, are probably the more promising way to move forward for right now in the field.
So let's thank Jen again.
Cool. Thank you very much.